recording. Okay, and I am going to change to my document camera and I'm going to pin myself. So what I'd like to do now is just go over the quiz quickly, just so we have a little bit more practice on 3D. So I'm reading through the problem at the top. They tell you what theta is. They tell you what phi is. They tell you what p is. So the first thing really you need to do is find the components of p. So that's what I did. P was given as 125. I found out what the y component is, which is right here. And I found out that the z component is right here. And there is no component of this force in the x direction. So how do I know this? Big thing for me that helps is parallel lines. Here is this force P. Its component is right here. This is parallel to the y-axis, so this is PY. Here, this line right here is parallel to the z, so I know it's PZ. And it is in the YZ plane. There is no component in the X. So when I'm trying to find the moment that the X component creates about 0.0, there is no moment because there is no force in the X. Then we also know that PY can't create a moment about Y because they're parallel. It can't cause the Y-axis to spin around its axis, or let me say, this Y force cannot cause this crank to spin about the Y-axis because the force is parallel to the Y. So I know the force Y creates no moment about the Y, and it's because it's parallel. And in the same situation, PZ can't make this thing spin around the Z-axis because it's parallel. So again, the FZ creates a zero force around the Z moment, the Z-axis going through O because it's parallel. Then the next thing, when I started looking at distances, it told me what the distance was from A to B. It was 200 millimeters. And I could see that this is a diagonal. It has a component in the Y. Again, I'm looking at parallel lines. And it has a component in the Z. And right here is, even though it may not look, if I took a protractor, I would not measure 90 degrees because this right here is lying in the YZ plane. But this line here is the Y, and this line is the Z. So this is perpendicular. So I have this triangle that has the, let's say, Y. It has the Y distance here, and it has the Z distance here. And I'm given that this distance is 200 millimeters. And it tells me that this angle right here is theta, and it's equal to 65. So I could find out what the Y value is and the Z value is with trig. And so I calculated it, and the Y value is 181.3, and the Z value is 84.5, and that's the Z value. If you find when you're doing a problem that you're getting stuck on the geometry, just call this Y and call this Z. Give it a variable and move on, because this is the statics part. I want to know you understand this part. This is trig that you should have from a long time ago, and it just means that you need to practice more on trig. Did everybody understand that? If you are finding the geometry is holding you up, use a variable for each one and move on. Don't let the geometry hang you up. But it does mean to you that you really need to practice more trig. Okay, so let's look at, actually, I'm just going to do it myself. So I'm looking at the force in the Y. So I'm looking at this right now, my force in the Y that's in this direction. So let's just use a highlighter. Here's my force in the Y. And I'm looking at the moment about the x-axis right here. And I'll use another highlighter. Here, right here is my x-axis. So I can see that Fy is in front of the x-axis. So the value of the moment about the x-axis is going to be the value of Fy times this perpendicular distance. The force is in the y, the distance is in the x. It's got to be the z distance. And does it create a positive or negative moment? Think about it. If the force is in front of the x-axis, it's pushing down on the x-axis right here, and it's causing it to spin like this. Fingers go in direction of the force, palm goes down towards y, my thumb is pointing in the x, I have a positive value. And what we talked about on Friday, no, not Friday, on Thursday, is another way to do it is stick your thumb in the positive x-axis and see if this force in front would create a positive spin. And if it does, it's positive. If it doesn't, it's going the other direction and it would be in the negative x. Now we're still looking at Fy, but now we're looking at the z-axis. This Fy is on the right side of the z. So we look at the force is Fy times, if this is the z-axis, the perpendicular distance I'm looking at is this plus this. So let's figure that out. The force is in the y, the moment is in the z, the distance has to be in the x. And where this is, the perpendicular distance is this full thing, 150 plus 100. 150 plus 100. And now let's think about it. Let me do it by the second way. I'm hoping everybody is paying attention, because I'm really just talking to a, I'm just talking, but I don't see anybody. So my second way is to put my thumb in the positive z-axis, and would this force that's on this side of the z create a positive moment? And it doesn't. It is causing it to spin in this direction, which is negative. Okay, let's do the other force now. So now we have, here is my force z, my force in the z, and I'm looking at the moment about the x. If the force z, and I'm trying to find the moment about the x-axis, if the force is in the z and the axis I'm trying to find the moment about is in the x, the distance has to be the y value. And this y value, it's 181.3. So this force C is on top of the x-axis. If I stick my finger, positive thumb in the positive x-axis, it does spin towards me and it's positive. And now let's look at the FZ around the y-axis, which is over here. Let me just find maybe a little bit different color. Here's my y-axis. So force Z. So I have the force Z. I'm trying to find the moment about the y. The distance has to be in the x. Here is the x distance again, because I'm looking at this to here. So it's this distance along the rod and then this distance along that handle. And that distance again is 150 plus 100. So is it positive or negative? Finger, if you want to do it by the second way, in order to create a moment about y, if it's positive, my thumb is here, it's got to be creating, if it creates a positive moment about the y, it's got to be spinning around the y like this. But the only way that can happen is if my force in my z is over here, but my force in the z is here. Fingers go in the direction of force, palm goes towards the axis, and it comes out to be a negative. And then you sum up all the moments about O in the X, sum up all the moments about O in the Y, sum up all the moments about Z. And then the problem says to represent the moment in vector form. So you have to represent it in I, J, K. We know that, though, that we could also represent the moment in magnitude and direction angle, but I didn't ask that. Whenever there's a moment problem, I'm always going to tell you exactly what I want to see. Okay, questions? Any questions? Okay. All right, I'm gonna change back to me setting of just me on the photo. I'm gonna go to gallery view. Everybody's with me, right? Give me a thumbs up. Are you starting to feel more comfortable in 3D right-hand rule? Okay, take your thumbs down, or I think they just kind of go away. And now give me a thumbs up. Is 3D right-hand rule getting better for you? All right. Okay, you want to do more and more problems. Okay, so the topic today is equivalent systems, and I really love this topic. And the reason why is I love taking something complicated and making and simplifying it. And that's what equivalent systems does. Now, I'm hoping that you all watched the video. Last night I watched the video and I realized that the video included 14 minutes actually of instruction. And then I did 3 problems to give you practice. So what I'm going to do is I'm going to review quickly. And then what I want us to do is work on the homework problems. So what this is called, you might have heard of it before, is flipping the classroom. It's having you watch the lecture outside of class and then doing the homework inside of class. And a lot of faculty at universities and engineering say it's a great way to go because you could watch the lecture, and then while you're doing the homework and you're having issues or problems, I'm here to help you. So I wanted to try it in this class because I'd really like to do it again if it's the method that you guys really like. And I will post the solutions to that homework with all the numbers, so you'll see it later on. So to start off, we're going to do a little review on what equivalent systems are. And please put in the chat just to me if you did not watch the video, if you did not watch the equivalent system video. Great. Okay, so a few of you didn't. Okay, you guys, in the future, you got to watch the video because it's like the homework. If you're not prepared for class, then I can't flip classrooms. And I think my guess is, as a student, when you're doing your homework, you have a question and you wish I was sitting right there, right? Don't you wish? And that's what we could do on flipping the classroom. Because I've taught this so many times that while I'm teaching, I know what your questions are going to be already. So I could usually predict what your questions are, and I do it in the video. But I can't predict your questions during homework because you guys always do it on your own. So if you truly want me to flip the classroom, you have to be committed to watching the video. Okay. Okay, I'm going back and I'm pinning myself again. And if you can't see it, then you should pin me. All right. So what we're going to do this quickly because I don't want to waste the time of the people who did watch the video. So there are systems that we can make that are a lot simpler than the problem. So let's take a look at this problem. Everybody with me? Everybody awake? Wide awake? 10:25, wide awake? Here is a beam that goes from A, B to C. There's a force going up 10 pounds at A, a force going down at 15 pounds at B, and 25 pounds going at C. This doesn't look like a complicated problem, and it's not so complicated, but we're going to see problems in statics that's way more complicated. The first thing is I want you to find the resultant of this system. And we know the resultant now means the resultant force and the resultant moment. So in order to find the resultant force, I'm going to add all these forces, and the resultant turns out to be 20 pounds. And the resultant is in the Y, and it's going up, which means the resultant movement of this beam is being pulled up 20 pounds by these three forces together. Then the other resultant is the moment. But in order to find the resultant in the moment, I need to find the point that I'm finding the moment about, and I'm going to find the moment about point A. If these were all couples, would I need to know the point I'm finding the moment about? Question again. If these were all couples, would I have to know the point I'm finding the moment about? And the answer is no. Right? No, because when there are a series of couples, all the forces are canceling out. So let's just take a quick look at it. There's a 10 here. There's a 15 here. And I could say the 15 is really a 10 down and a 5 down. So I could say, sure, there's a couple, there's a 10 and a 10. And then I could look at this 5 going down and, oh, well, there's a 25. I could say this is a 20 and a 5 going up, and the 5s cancel. So you could say there's a 10-pound couple and a 5-pound couple, but there's still a 20-pound couple here. So this does not result in a couple, a series of couples, which means then that there is a moment. And I have to choose a point I have to find the moment about. And I found that it creates a 150 foot-pound rotation about point A. So an equivalent system to this problem here is creating something, and this is called a force moment problem. I could put the 20 pounds at point A, and I could put the moment directly at point A. And this system now, with a concentrated force and a concentrated moment at A, will have the same net effect of this. We determined that this beam from these three forces are going up 20 by 20 pounds, and they're spinning around A of 150. If I instead remove these forces, but instead put a 20-pound force going up and put a 155 moment about A, it's the same net effect. It's pushing it 20 pounds up, and it's spinning at 155. This is called an equivalent system. It's equivalent force moment problem. And this is what I call it. I call it a force moment problem because the problem is asking you to find an equivalent system, simplify this problem by putting one force and one moment at a point. The other equivalent system is called a force location problem. What if I took this 20 pounds and I put it out a certain distance? Couldn't I create a 155 foot-pound moment about A? Sure, I could find what the distance is. I know that the resultant moment is 155, right? So I solve for the moment. I could take, we know that a moment is equal to the absolute value of the force times the absolute value of the perpendicular distance. So if I wanted to know what the perpendicular distance is from that 20-pound force, I could say divide the moment by the force. So it turns out to be 155 divided by 20, and the perpendicular distance comes out to be 7.75 feet. So if I locate 20 pounds at a distance on the beam and divide the 155 foot-pound moment by the 20 pounds, I could find the distance that I could stick this 20 pounds that creates the same resultant. This force at 7.75 feet away from A causes the beam to move up and spin at A, 155 foot-pounds. This is called a force location problem because I'm asking you to put an equivalent force at a distance, at a location that creates the same net effect resultant of force and moments. Okay, I want to check in with everybody. So those of you who already watched the video just saw it for a second time, so you're probably more comfortable. Does somebody have a question? We're taking a complicated problem and we're reducing it to two simplified systems. So now we have three ways to represent something. So now I want to do one more problem because, and where did I put it? Okay, I don't know where I put it, so we're going to make up a problem. Okay. So I'm putting it back on here. I'm pinning myself again, and you probably have to go into the speaker view or pin me. So now we have a beam. Here's A, here's B, here's C, here's D. And the reason why I want to do this problem is I'm going to put in something here. Let's actually, let's do it a little bit differently. Let's say this is 15 pounds and this is 25 pounds and this is 100. This is, it's not drawn to scale NTS, not to scale 3, 2, 1. Okay, I want to use different numbers. Sorry, I drew it not so great. So this is going to be foot pounds. Okay, first thing I want to remind you, I know we talked about this in class before, and now I'm going to start going through you guys. Actually, I think I'm just going to teach I'm going to answer questions and not go around the room because we're going to run out of time. So take a look at how I drew this arrow. It does not look like this. And it does not look like that, right? This is it's spinning forward. This one is it's spinning back. Can you see that this drawing of the curve is not these two? This is called, just like this, we know is a concentrated force. This is called a concentrated moment. You need to know this word. And I know we mentioned it once before. What is this like? It's like me taking a screwdriver, sticking it at B and turning it, or sticking this top right here and turning it. It's really applying a couple, but I'm not giving you the two force values. Instead, I'm giving you the moment. So this is not so much a complicated problem, but let's see, this is 15 pounds and I want to get more practice using couples. So I'm going to cross this out and say it's 15 pounds and 10 pounds together. So I could say that if I apply a 15-pound force going up and a 10-pound force going up at D, it's the same as 25. So now I want to find out what the resultant force is. Let me call it RF. So RF, it's going to be negative 15. Well, actually, I don't even need to do that, right? I could say negative 15 plus 15 plus 10, but I don't need to do that because I know these two right here are couples and the resultant from couples in forces is 0. That's all this is 10 pounds and it's going up. And now how about the resultant moment? Do I have to specify a point I'm finding my moment about? And the answer is yes, because there is a force here that is not part of the couple and can create a moment about any point. So we know with couples, it's 15 times the perpendicular distance between and we know we could go like that. We know it's going to be positive in the Z. And then I have a 10 pound, that's 6 away from A. And my fingers go in the direction of force, palm goes towards A. It's positive. And what's this coming out to be? 60 plus 15. So it's 75 foot-pound. And it's in the K. And it's positive. So whether I do a force moment problem or a force location problem, regardless whether I want my result to be a force and a moment at a point or a force at a distance, I first have to find the force, the resultant force, and I have to find the resultant moment. I left something out here. Isn't there another spin, another moment that's going on in this problem? There is a concentrated moment that I totally overlooked. I have to remember that the concentrated moment has to be put in. No matter where I'm finding my moment about, I have to add in that concentrated moment. So where did we say we were finding the moment about? Point A. I have to remember to put in the concentrated moment, and it's in the positive Z direction. So this is not 75. This is 175. And no matter if I found the moment about A, even, okay, this is an aside. Let's just do it. I have to find the resultant moment about B. I still have the 100 in there. The 15 does not create. The 15 does not couple, does not create. Oh, sorry, it creates. I don't have to go all the way back. It's just times 1. It's positive. And then I have the 10 times 3, and it's positive. So the resultant moment about B comes out to be 30, 45, 145 foot-pound, and it's in the K, and it's positive. So this is a very tricky thing. And I want to introduce this, and I didn't talk much about, I don't think I talked about this in the video at all. So everybody's with me, right? Everybody's with me? When you have a concentrated moment, no matter which point you're trying to find, you have to add the concentrated moment into any moment equation. Okay, now, if you weren't listening, you got to listen again. I'm going to say it again, because typically 10 people out of 30 get this wrong on the exam. You always have to add in the 100 pounds. Why? Because I am sticking a screwdriver in here and I am spinning this thing at 100 foot-pounds. So even though this 100 foot-pounds is at B, and you normally think, well, if a force goes through a point, it doesn't create a moment. That is true. But if I put a screwdriver here and spin it, it is going to cause a spin about B. So even though a concentrated moment is at a point, it's going to get a spin. Another way to think about it, the textbook calls these couples. I don't like that. I don't like that they call it a couple, because to me, the definition of couple is two forces, same magnitude in opposite direction, but they do that because they know that when you apply a force on a top or even a screwdriver, you are putting one force going in this direction and you're putting the other, it's really a couple. So you could think about it that when you have a couple, no matter where you have a couple, it's going to create a moment. So any questions? This was an aside, but it's very important for you to understand the topic of concentrated moments. You have to put the moment in any moment equation. So you guys, I'm going to go over on class, and maybe I should have asked you first, but I'm going to take it back and say, Do you want extra time on your quiz? Well, if you want extra time in your quiz, you're going to have to stay in class longer. So I'm going to assume you would have said the answer is yes. So force moment problem means I need a force and a moment at a point. And what point was in question? It was A. Here's A. Here's B. Let me draw it. Here's C. And here's D. And a force moment, that's all I do is at A, I put the resultant force, which we found is 10 pounds going up, and I draw the moment, and I'm going to put 175 foot-pounds. And this is what, 3 feet, 2 feet, 1 foot. That's a force moment problem. You find no matter whether you're doing a force moment problem or a force location problem, the first step, find the resultant force. Step 2, find the resultant moment. In a force moment problem, the next step is just draw the force and the moment on the beam. Force location problem, the next step, I have to find the perpendicular distance, which is the moment over the force, which is 175. Remember, this is an aside because I want to find it about A over 10. So the perpendicular distance is 17.5 feet. And now up, I draw the beam. Here's A, B, C, D, A, B, C, D, 3, 2, 1. And where is the force? The force goes up 10 pounds, and the distance is 17.5 feet.
Can you move the camera down, Joanne?
Yep, thanks, Olivia. So even though this totally looks weird, how the hell could I put a force on a beam when I'm not even touching it? Well, there's got to be some way that you're touching it. You are applying a force. Maybe you're using a torque wrench. Maybe you're putting a wrench out here with a string. Who knows? But you are drawing the force at the distance. So to sum it up, for a force moment problem, and look at this, force moment problem, step 1 is find the resultant force. Force moment problem, step 2 is find the resultant moment. Step 3 for a force moment problem is to draw the force and the moment. For a force location problem, step 1 is to find the resultant force. Step 2 for the force location is find the resultant moment. Step 3 for a force location problem is find the perpendicular distance. And step 4 for a force location problem is draw the beam with the force at the distance. I'm not just talking about this here. I'm also, and this will be posted, I'm also talking about it on the video, and it's also in the overview for these two types of problems. All right. The next thing I did on the video, I'm not going to do now. What I did is I went over 3 different problems. And these are the 3 different problems. So let's just read the words, but we're not going to do it. It says, replace the 3 forces shown by an equivalent force couple system at point B. So is this a force moment problem or is it a force location problem? Remember that the textbook likes the word couple to mean a concentrated moment. So they're asking you to replace these three forces by an equivalent force couple system. This is a force moment problem. Find the resultant force, find the resultant moment, draw both of them at point B. Next problem, that was a 2D problem. Now it's a 3D problem. Determine the resultant of the parallel force system shown below and locate the intersection of the line of action of the resultant with the XY plane. So they want you to find the resultant, which means resultant force and resultant moment. And they're asking you to locate the resultant force and put it on here. This is a force location problem. This problem, you're not going to have a problem with because we just did one and you've seen a bunch. 3D problems are harder, just like normal. These forces are not creating a moment about Z because they're parallel to the Z, but all 4 of these forces are creating a moment about X, and 3 of these forces are creating a moment about Y. So you have to watch the video to see the solution of this problem. Next problem, forces are applied at point A, B, and C, another 3D problem of the bar shown. Replace this system of forces with a force R through point O and a couple. Again, this is called a force moment problem. They want you to draw the resultant force and a couple. Hang on. You can't. This might make you confused here. You notice this C is bold. They're calling it C. They're not talking about point C. You got to read it close. Replace this system of forces with a force R through point O. This is the point they want you to find the moment and the resultant at. But this is a force moment problem. Here, in these 2 problems, you're going to get more practice in drawing 3D problems. And I know from the last quiz, I know from the last exam that half of you still need more practice drawing things in 3D. So you're going to get an opportunity because we know that in a force location problem, basically each one of these force moment problems and force location problems, the last thing you have to do is draw it. So yes, you're going to have to draw an easy 3D bar, but then you're going to have to draw a hard 3D plane. Well, that's not as hard as drawing this 3D bar here. Okay, so now the point we're at now is now I would like to look at the homework problems. And now I am going to go around the room. I never know where I stop, and I should probably have you guys, you know what, from now on, you remember who the last person was, okay? Because I'm probably calling on more people, same people a lot more. So let me go into the homework. And let me just share the screen. And it would be nice if I didn't have my textbook all marked up, but I do. Because I do. So could somebody look at the numbers on the homework? So I'm talking about homework 15 and 16. So on homework 15, the first problem is 3.84a. Actually, it's okay. I don't need to see. I'll just look at this. Okay. So here, can everybody see my screen? I mean, I'm sorry. Can everybody see my textbook? I'm not hearing anybody.
Yeah.
I can see it, but not 3 point. Did you say 3.84a?
3.84a. Could you see it now?
I think it's below the blimp.
Okay, I guess I do need you. I need you to tell me which number so I could see my own book. Okay. Okay. So I only want you to do A. It says, and here's the problem. Is it a 2D? Okay, let's start with Keith. Keith, is 84 a 2D or a 3D problem?
2D.
2D. Okay, Keith, Lukey, you're next. 30-pound vertical force P, so that's that guy right there, is applied at A to a bracket shown, which is held by a screw at B and C. Replace P with an equivalent force couple system at point B. So Lukey, is this a force moment problem or a force location problem?
Force moment.
Force moment, and they want you to find the equivalent force moment at B. So, Mackenzie, what do you do first on these problems? First, you find Kenzie,
Find the
resultant force, then
find the moment.
resultant moment. Then, since this is a force moment system, what's the third step on a force moment problem?
You draw the
I draw this bar. Just draw the bar. Don't draw the wall too, because the bar is what's in question, right?
Mhm.
So you draw the bar and then you draw the force and the moment at B. Great. Okay, Makana, you're next. The next problem is it 89A?
Yeah.
Okay, so 39A. 89, is this a 2D or a 3D problem? Makana,
2D.
great. Manny, you're next. 3 control rods. 1, 2, 3. Oh, no, 1, 2, 3. So one is a rod, another rod, and this one's more like an L bracket. 3 control rods attached to a lever. Exert on the forces shown. Replace the 3 forces with equivalent force couple system at B. So what kind of problem is this? Manny? Okay, Max? Force moment problem or force location problem? Replace the 3 forces with an equivalent force couple system at B.
Yeah. So sorry. What was the question specifically?
I'm gonna skip you, Max.
Okay.
Nico? It says replace the 3 forces with an equivalent force couple system at B. Is it a force moment problem or a force location?
A force moment problem.
Right, what's the steps? Step 1,
Step 1, find the resultant
force. Step
force.
2,
Yeah,
resultant
moment.
moment. Step 3,
Draw them.
draw it and put the force in the moment at B. Let's just see. Let's do 89B. I don't think you have to do it for homework, but it says, and now I'm on Olivia. Determine the single force that is equivalent to the force couple system obtained in part A and specify its point of application on the lever. What kind of problem is that? Olivia? Okay, Othello?
That sounds like a force location.
Correct, because they're asking you to find the point of application. So Othello,
Okay.
what are the steps in a force location problem?
So force location problem, first you would find the resultant of the
Resultant
forces.
force, the resultant moment,
Moment.
then
You would find the distance between, so how would I call that? The parallel distance?
the perpendicular.
Or sorry,
I
yeah,
would find the
distance.
perpendicular distance,
Right,
and then the fourth
draw
step is to
draw it at the
draw the
location.
one force at that distance.
Right.
Great. What's the next problem? And Ryan, you're on next.
It's 113, Joanne.
Thank you. Ryan, are you here?
Yeah.
Okay, 113, still 2D problem, right?
Yeah.
It says a truss supports the loading shown. Determine the equivalent force acting on the truss at the point of intersection of its line of action with the line perpendicular from A. I changed the wording and you'll see that on the question. So what type of problem is this? Force moment or force location?
Force moment.
They're asking you for the point of intersection of the line of action.
Okay, so we need a,
It's got to
Force
be a
location.
force location problem because they're asking you for a distance.
gotcha.
Okay. Okay, so what are the 4 steps? Find the resultant force, find the resultant moment, draw the picture. Sorry, 3rd step for a force location, calculate the perpendicular distance. And the 4th step is draw the structure, show the force at a certain distance. Okay, what's the next problem? Is that the last one?
For homework 15, yeah. But
Okay, what's 16? Aaliyah, what's the next one?
3.95.
Okay, 9.5. So Sam, here's the problem here. It's set, first of all, 2D or 3D,
3D.
right? Replace the 150 Newton force with the equivalent force couple at A. So they want to find what's happening up here. Is this a force location or a force moment problem?
Force moment.
Correct. And what are the steps? Find
The resultant force.
result. Next step,
The resultant moment.
about what point?
At A
Great. And then the 3rd step,
is to draw it on the whatever that is. On the
draw
graph.
it. Draw it right at point A. Okay, and draw the bracket so you get more practice on the bracket. Okay, Thea, you're next. And Aaliyah, what's the next problem? Is it 98?
It's 127.
Thank you. Okay, I'm going to end class pretty soon. So we're not getting an opportunity. Well, I'm going to talk to you at the beginning, at the end. Okay, Thea, 2D or 3D problem? Alex. Aaliyah, 2D or 3D?
3D.
3D. 3 children are standing on the raft. If the weight of the children respectively determine the magnitude and the point of application of the resultant of the 3 weights. What is a force moment, force location?
Force location.
Force location. So what are the steps? Step 1,
You find the force.
resultant force.
Yeah. And then you
Second
find
step.
the resultant moment. And then
Third
you
step.
solve for the perpendicular distance.
Distance, and it's 3D. It's going to be, this is going to be a 3, you're going to have 2 distances. And then 4 is?
You draw it.
Draw
You
it.
draw it. Yeah.
Great. Draw the one force, the resultant force at the distance. I think you're getting a hang of this. Although I, didn't go around the room much.